Hello, my name is Brian Olson. My project is on increasing power grid network robustness with optimal transmission line placement. So the motivation behind this project is there has been increased funding and attention towards securing power grid and its many inefficiencies. The U.S. presidential budget plan, for example, has announced $13 billion in funding to modernize the U.S. power grid. Substations targeted for extremist attacks have become more common. Increasing power demands and shortages will only increase given population flux, and power grid failures have increased primarily because of weather-related events, also tying into the theme-related issue for this year's hackathon. So the problem statement is the problem complexity of evaluating power grids fault points typically range from NP hard to NP complete problems, and we need to reevaluate new transmission line placement for securing those fault points. So that means it's extremely difficult to solve, and we are constrained in evaluating optimal changes for the power grid. The data set was created from the U.S. Western Interconnection Power Grid Network from the provided Wolfram Alpha Data Repository from the Wolfram 1 account that was also provided from the Caltech Hackathon. So this network is an undirected, unweighted network, and this is the most basic data you can get about a power grid. So some pre-processing. As mentioned earlier, the problem complexity of any network-based problem typically explodes. So how to address this is you can reduce the dimensionality with some logical basis, and or you can map to a cubo problem or a quadratically unconstrained binary optimization problem. So first, reducing your dimensionality with logical basis kind of looks like this. You use common centrality metrics, like utilizing the very common network X library to find central or influential nodes. And we'll call those nodes the generators in a power grid network because, i.e., a generator should be highly connected in a power grid network by a bunch of consumers. And then you return the nodes that all three metrics corroborate on. So as you can see, this is just like some correlation table saying that they do corroborate on something, so we should at least check where they intersect, and you return those as the generators to actually look at. So some more pre-processing is that this problem can actually be mapped as a maximum click cover problem, which is also a quadratically unconstrained binary optimization problem, which matters because even though I could only have solved this with classical computing resources, given that I'm only running this on my laptop, you could scale this algorithm to running onto a quantum computer by mapping the eigenvector centrality metric, which is also a cubo problem, and the maximum click cover problem, which is also a cubo problem. So that way we observe the performance changes by using the highly parallelized hardware that we have available. So once a maximum click is covered, you remove that subgraph and cursorily perform the solver. 8 through 13 or 9 through 14 are susceptible, as you can see. So those are nodes that are connected, or very weakly connected to the rest of them. That's why they weren't covered in the rest of the clicks from 0 to 7, the rest of the maximal clicks. So that's why I'm deeming these the high priority nodes, or the ones that we have to look at to add more connections to. Otherwise, they will fail and not have any securing or redirection of power. So to clarify, with the high priority nodes being highlighted and dimension C value being minimized, I impose two constraints for placing new transmission lines. The distances from one generator's linking must be less than 3 nodes length, and if a generator forms a loop with itself, to append entirely new edges to adjacent generators. In the code, this exception is node 2553, i.e. it forms a loop with itself. So the result, I implement a method for testing and cascading failure for the network, and the before and after changes are significant. Before there were 169, after there were 62, so a 63% decrease in the shutdowns. Thank you for listening to my project, and I hope you have a great day.